We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Good morning, students. I am Professor MIHIR VASAVADA, Department of Electrical Engineering, LD College of Engineering. Okay, very good morning to all students. As during our classes, we have covered all the topics related to design of DC machine. We have covered the output equation, main dimension, the numericals, the factors affecting selection of number of poles, length of air gap. We have also discussed about the armature reaction, its effects, right? A bit about commutation also. Now this is one topic, that is the field winding design is remaining. It's a major topic, so I am going to cover this. That is the design of shunt field winding. Now what is field winding? The function of the field winding in DC machine is to produce the main field flux in the machine, right? It consists of actually 2 main things. One is field poles and field winding, right? Field pole consists of pole body and pole shoe, and surrounding that the field winding is wound. So actually field system consists of an electromagnetic type of field winding. Now there are 2 types of field winding, either shunt field winding or series field winding. As you know, in shunt field winding, the winding is connected across the armature. So shunt field winding and armature winding both are connected in parallel. Shunt field winding is made up of large number of turns. It has to carry small current. So obviously the cross-sectional area is less. Series field winding, as you all know, is connected in series with the armature. So it has to carry your entire armature current or load current. So it is to be made up of thick cross-section area, thick conductors or strips, and it is made up of few number of turns, right? Now this is actually the stator of the DC machine. As you can see, this is the pole shoe laminated, which is visible here, and the pole body is surrounded by the field winding, right? So this is the stator of DC machine. Now field coils. The field coils are former wound and they are placed over the poles, as we have discussed. The field coils may be of rectangular shape or a circular cross section area, depending upon the type of the pole. There are main dimension of the field coil, that is LMT, length of mean turn of the field winding, depth of the field winding, which depends upon the armature, and height of the field winding, which depends upon the surface required for pulling of the coil, and the number of turns. Now HF and TF, these 2 cannot be independently designed. They are depending upon the each other. So these field coils are generally made up of copper, right? In actually the insulation, most common insulation is varnish, right? As we have discussed, the cross section of the field winding conductors are either round or rectangular, right? Now field coils which are placed on the field poles, they are connected in series with each other, right? And they are designed for 80 to 85% of the excitation voltage, because the rest remaining 10 to 25% of the excitation voltage is across the field regulator or field rheostat. Now what is the field regulator or field rheostat? The field rheostat is a rheostat connected in series with the field. And what is the function? Yes, its function is to control the field current, hence it will control the flux. So control of the flux will control your voltage if it is a generator and speed if it is a motor, right? Now what will be the outcome of the design of the shunt field winding? So it consists of multi-step process. Outcome means you will be getting the dimension of the field pole. There are 2 separate things, field pole and field winding. So dimension of the main field pole you are getting, then dimension of the field coil, and then you will be getting the current in the shunt field winding, resistance of the shunt field coil, dimension of the shunt field winding, right? Number of turns in the shunt field coil, and the most important, losses of the shunt field coil, right? Now there are two actually main types of field coils, either rectangular field poles or for cylindrical poles. If the field poles are rectangular, then we need to find out the cross-sectional area of the pole, length of the pole, width of the pole body, and height of the pole body. But if the pole is circular, cylindrical, then you need to find out the cross-sectional area and obviously the diameter of the field pole, right? Now, first step, that is design of the field pole, right? The dimension of the field pole. So, in order to find out the area of the pole body, you need to find out what is the area required for the pole body. So, for that, you need to find out the flux. What is the working flux required in your DC machine, right? Working flux estimate can be you are getting from the output. Which type of voltage you need, what is your power output, what is your torque output, that will decide the flux. Once the flux is decided, you have to consider the leakage coefficient and find out the flux per pole, that is phi p, leakage coefficient into the flux, right? Now assume the flux density in the pole in the range of 1.2 to 1.7 Tesla. This is as per the data available in the field, right? So once you are assuming the density value of the flux density, you can easily find out the area of the flux pole, right? So area is actually flux divided by the assumed flux density, right? Now there are two options, circular poles or rectangular poles. If you go with circular poles, then obviously the area of a circle is pi by 4 d square. Now you know the area, so easily you can find out the diameter, right? That is square root of 4 into area divided by the pi. Now if the field pole is rectangular, right, then you have to choose the length of the pole. Then the dimension requirement is the length of the pole, width of the pole, and height, right? So length of the pole chosen is 10 to 15 mm less than that of the length of the armature, right? So length of the armature, that is L, that we are getting after solving the main dimension problem, D and L. So length of the pole is either minus or plus 10 to 15 mm less, generally 10 to 15 mm less than the length of the armature. Once you get the length of the pole, you have to consider the net iron length by considering the 0.9. What is that? Yes, stacking factor. Then width of the pole obviously is the area of the pole divided by the net iron length, that will give you the width of the pole. Now what is the height of the pole body? The height of the pole body is height of the field winding plus thickness of insulation and clearance, right? So in case of field pole, whether it's a circular or rectangular, you can find out all the dimension. Now the second important part, that is the design or dimension of the field winding. So the task is to find out the length of mean turn for the shunt field coil, because when you wound the first winding around the pole, first turn, it is having the least length. If it's circular, consider the first circle having the length, minimum length of mean turn. Then the second one is higher than that, and outermost is the maximum length of mean turn. So for obviously cylindrical or circular coil, you can tell that it is LMT is the length of mean turn, pi into d, right? And if it is a rectangular coil, it is simple, it is LO plus Li by 2. Now as we have discussed already, to find out the voltage across each shunt field coil, right? So the total voltage, applied voltage, excitation voltage is V. Out of that we have to consider 80 to 85% of the voltage. So that is V into 0.8 or 0.85 V will give you the voltage across total number of field coils, and all these field coils are across the number of poles. So voltage across each shunt field coil is divided by number of poles. Clear? Because remaining 10 to 15% voltage is across the field regulator, right? So once you get this EF, next task is to find out the cross section area. How to find out? So for that, this equation is useful actually. It is EF, that is the voltage across the each shunt field coil is equal to the shunt field current IF, right, into the resistance of shunt field winding, right? EF equal to IF into RF. Now what is the equation for the resistance of any conductor? That is RF. So RF is equal to the rho. Rho is the resistivity of the conducting material used for the shunt field winding, rho, right, into the length. That is, length here is LMT. So it is length of mean turn divided by area of shunt field, right, rho L over A. So this value of RF, you put it over here. So it is EF equal to IF into rho LMT upon AF, right? In this equation, if you make AF, what we are interested to find out area. So in this equation, if you put make AF subject to the formula here, then this equation will come, right? So AF equals to rho LMT, right, into IF, right, upon AF. Clear? So this will be the equation of area of the shunt field winding. Once you get the area, if you assume the conductor is always a circular, so circle area is pi by 4d square. So from that equation you can find out the diameter, square root of 4a upon pi, right? And then once you find out the diameter, you have to consider the thickness of insulation also. So this will be including the insulation thickness. And what is the space factor? You have to consider the space factor also, so that is 0.75 here, right? So this is the finding out of next step is to calculate the field excitation current, IF, right? So for that means recalculate. So you have to assume the current density, right? So current density should be 1.522 ampere per mm square for the shunt field winding used. So once you assume any value out of this, you can find out the current, actual current in the field winding, AF into delta F, right? Once you got this, you can calculate the number of turns TF, so that is AT by IF. Then calculate the AT. AT is IF into TF, what we have calculated in step 6 and step 7. That will give you the AT actual. Now what is the actual AT desired? Sorry, what is the AT desired? So it is 1.1 to 1.25 times the armature MMF full load. So once you know the armature MMF at full load, you have to multiply it with 1.1 to 1.25 factor and find out the AT desired. If your AT actual exceeds the AT desired, then you need to increase the depth of field winding by 5% and process again, right? Now important step is power loss. So what is power loss? As you know, power loss is the I square R loss in the shunt field winding, which depends upon the resistance of the winding and current flowing through the winding, right? The heat is developed when the current is passing through the shunt field winding, right? So what we need to do, we need to find out the actual copper loss, IF square RF, right? Now what is the total surface area? Surface area is heat dissipating surface area. So if we consider all the surfaces, that is inner surface, outer surface, top and bottom surface, then the equation of surface dissipating area is this. Considering that, you can easily find out the cooling coefficient, which is equation is already known to you. You learned in the basic of elements of electrical design, right? And from that you can find out the temperature rise, theta m. If temperature rise is within the limit, then there is no issue. But if it exceeds any limit, if it is more than the limit, now what is the limit of temperature rise? It depends upon the insulating material you used, which class you used. That will decide your temperature rise limit. Class Y, class A, you know that the value, right? So if it is within the limit, there is no issue. But if it is outside the limit, then you need to increase the depth of the field winding by 5% and proceed again. So these are the limiting or the checks which you need to perform, right? So this completes our overall design of shunt field winding. Thank you, students. My email address is mihir75@ldc.ac.in. YouTube channel details is also in the slide. Thank you.